file, I'm going to save as example 9. And for example 9, what we want to do is build a 1D decision boundary for the iris dataset. Example 9, so 1D decision boundary. All right, so to do that, I guess I need to let's define what we're going to train it on, right? So let's go train a logistic regression model. And don't get confused that we're not training a classifier, right? We're training a regression model, and then we're using it for classification. So let's define the features and of X and the output Y, because for us, we're going to only concerned about some of that. So we're going to go X underscore petal is equal to iris data. All of my rows for column 3 to the end. That'll give me, and I'm going to go, I want a capital X there. Here I'm going to go lowercase y because I've kind of moved down to a subset. Underscore petal is equal to iris. I need to put, I'm going to put this in a tuple. Iris, iris target is equal to 2. And that should give me a data set and a target. So now let's build a model based on that. So we're going to build a logistic regression model. Log underscore regression equals to sk.linear underscore model dot logistic regression. I have an extra model dot logistic. There we go. It likes it now. Perfect. We're going to go C is equal to 1, and that's our cost function for how much we scale that. So log underscore regression dot fit X underscore petal, comma Y underscore petal.
Using capital X.
I did, didn't I? Okay. And now let's go ahead and build the range of the features to predict over. And that's going to look a little bit like this. So x underscore new is equal to np dot linspace of 0, 3, 1000. And then we're going to go x underscore new is equal to np dot expand, whoop, no capital E, dimensions. It's going to be x underscore new, comma, axis equals to 1. And then use the logistic regression model to predict the type of petal. So we're going to go y underscore prob equals log underscore regression dot predict underscore p. So they call it prob a. So I'm going to call it prob a just to keep standards. X underscore new. And let's see what happens if I hit F5. All right, everything is running, so not going to worry about it too much. And now let's try to plot out our results, right? So I'm going to go plt.figure, plt.grid true, and now I'm going to go plt.scatter. I'm just going to use the training set for 0 and 1. So that's going to look like capital X square bracket, capital Y is double equal to 0. Actually, I guess I could copy it. I could copy it from above, but I'm just going to type it out. But if you want to copy it from above, you can do that. 0, 3, comma, np dot zeros, because we just want it to be on our axes, bottom or high. We're just trying to remake that plot that we drew in before. And np dot zeros, oops, curly bracket of 50s, because that's how many data sets we have, comma, marker is equal to 0, comma, label is equal to y underscore names 0, comma, z order is equal to 10. And it almost fits on one line. We're going to see what our figure looks like. Okay, so we have a figure. Not quite sure that's what we want, but no, that actually looks pretty good. So now we need to do this for our other data set. So I'm going to copy this line. All right, what's the next data we want? We want the next species, but we still want the same feature. And then we want NP zeros, but now our marker is going to be square, and our names are going to be 1 because we're in the next species. And then we want to come to the last species, 2, still 50, but now our markers is going to be a diamond, and our name's going to be 2. But instead of zeros, we want this to be 1s because we are training it on 0s and 1s. There we go. And so that's what our data set looks like. Again, we are only thinking about plt.x label And it's going to be petal width in units of a centimeter. And I need a plt.y label. I'm just going to copy it over. And that's going to be probability. So now I've got petal width versus probability. All right, so this is just my data, right? These are just kind of my feature plots, but in one dimension, and I'm only looking at petal width. And then I've assigned the data to the top and bottom as 0 and 1, because everything at the 0 is not the species that we're trying to predict, versicolor, and everything at a 1 is a species we want to predict. So now we need to put in the model that we trained. So let's go ahead and let's go plot the probability. It's plt.plot x underscore new comma y underscore proba. And that's going to be everything for column 0, comma, dash dash for my line type, comma label is equal to not Iris virginsia. I hit F5. All right, so now I have this nice model, and basically it says at about 3 centimeters, I can predict that anything at 3 centimeters is very much not an Iris virginsia. So now I just need to plot the inverse of this. And I can do that by doing plt.plot make this from 0 to 1, and now I can plot Iris virginsia. And this is just the probability that I believe what I'm plotting out is Iris virginsia. Okay, one slight issue I have with this is I don't like the color scheme, because I've got orange and I have orange again, but my Iris virginsia is green. So I'm gonna adjust the color scheme. Does that make sense? It's a little bit workaroundy in Python. There's a couple different ways to do it, but this way is relatively straightforward. So I'm going to come up here to the very top, and I'm going to define a string that just extracts all of the colors for whatever color map I choose. So in theory, if you chose a different color map, this would adjust as needed. I'm going to go CC, it's just a list of my colors, is equal to PLT dot RC params, PARAMS. Now I'm going to I need to feed it a string for AXES dot prop underscore cycle. All right, so that's going to give me a bunch of keys, everything related to my plots, but that's not really what I want. So I'm going to go dot by underscore key, open and close that tuple. That still gives me a lot of things, and I'm just going to go COLOR. And in theory, that gives me a list that gives me the 10 colors to my color code. That's all it does, right? Those are kind of the color codes that I have. And now what I can do is I just want a nice colored plot that follows a pattern. So I'm going to come down here after my line and go CC is equal, well, I'm going to go CC is equal to 3, because that's what I'm trying to predict. And then for the second one, I'm going to go CC is equal to 2, although technically maybe Line 2D has no attribute CC. Oh, sorry. This is absolutely wrong. I need to go color is equal to CC3. And color is equal to CC2. Okay. So that looks a little bit better. Now let's go ahead. And so what I've got here is a green line that lines up with my iris mergensia. I'm just trying to make the plot prettier. And then a red line that matches up if it's not. Yeah.
I made an error. It says RT params object. It's not callable. It was lowercase r, lowercase c, and then capital P.
Yeah.
Okay, so that's wrong. Thank you.
So I want to put a legend in. Everyone needs a legend, right? plt.legend. So hardly the hardest piece of code that we're doing. All right, now I've got a nice legend. I've got iris mergensia, not iris mergensia. And now I want to find and plot the 50% decision boundary. Now that's not actually hard to do in a picture, but we want to do it in code. So we're going to go x_at_50 is equal to x_new np.argmin. That gets you the position of the minimum value of np.abs. It's the absolute value of y_proba, which is our probabilities that we estimated for 0, which is our not iris mergensia column, although technically you could use either one, minus 0.5. So when it's 0.5, 0.5 minus 0.5 is 0, and an argmin will get you the position of that, which is what x at 50 will get you. So x at 50 now just says 1.66 centimeters is our division line. So we can add that to our plot, plt.vlaines x_at_50, comma 0, comma 1, comma color equals k, line styles is equal to semicolons, comma label is equal to decision boundary. There's a nice vertical line that is our decision boundary. I guess if I put the legend below that, it'll pick that up. All right, so we have trained a logistic regression model for this. Now, what if we just want to make an arbitrary prediction, right? So if we want to just make an arbitrary prediction, we can do that with the log_regression.predict. Now you can't just feed it a value, you have to feed it a list of lists. A little weird, I know, but so square brackets, let's go. What do you want to predict? 1.7. So 1.7 should be a little bit to the right here. And it says if you have something, log predict, go print. Okay, prints out a true. So it says a 1.7 is an iris Ergensia. And if I have a 1.0, it should print out a false. So if you wanted to build a classifier on just your petal width, that is how you would do that. You think building classifiers on just one parameters is intelligent? But we have 4 parameters, right? So next we will look at how to do classifiers on kind of a multi-parameter system and plot those out.